and then I will assign the block after add drop. Block one से किस block से
first block
block one सारी block one से So after add drop, we will assign the block one more time. The tendency which I have circulated that was before add drop. So after add drop, I think there are around 20 to 25 new students joining. So we will be rearranging your numbers and other things after add drop. Which number you have to get? You are sitting at 1 to 14 block 1 from 41 to 18 class. Alright, so let's start with what we have left in the last class. In the last class, we started looking at the models. Before that, I have already put 100 slides in this course. So that is the tentative syllabus till your minor one. Isn't it? So the slides are already there in the book. You can get the hard copy of the slides. You can get the print of it. No soft copy will be sent to you. Okay? Alright? If you wanted to get these slides, you can get it from this book. That is what I am saying. Okay. So in the last class we started looking at the model. We said that process control, if you look at, primarily the process control is called upon to achieve three important tasks: suppressing the effect of disturbances on the system, making the inherently unstable system stable, and third one is to optimize the process. Correct. These are the three requirements. Then we said, in order to achieve these objectives and also in order to satisfy several constraints those are present in operation, you need to monitor different variables, isn't it? Correct. And if these variables are deviating from their set point value, in that case you are going to add the external intervention in the form of control. Okay. So for this external intervention, you need to know your system well. So knowing the system means what? Either you can know your system by performing several experiments and then get the feel of your experiment and do the modification accordingly. That is one way of doing it. That is called an experimental way of controlling, isn't it? Another approach is the theoretical approach, in which what we are saying is very often we have to design the control system even before the experimental setup is available. That is what happens in most of the plants, isn't it? You are designing the entire control system even before the plant is there. In such cases, you have to rely on mathematical equations. So you are representing the given system in terms of mathematical equations. Typically, these are comprising differential equations and algebraic equations. And you can solve these differential and algebraic equations in order to get the state of the system. When I am saying state of the system means what? I wanted to know how different variables are varying with respect to time. If there is a change in the disturbance variable or if there is a change in the manipulated variable. So this is what we are calling it as knowing the state of the system at any time. Okay. So to get these equations, typically we solve the balance equations, and these balance equations are like mass balance, component balance, energy balance and momentum balance. This we have already seen in the last class. We said that mostly mass balance, component balance and energy balance is used in process control. We don't use the momentum balance. But we have seen all these balance equations earlier in your different courses, and that is the reason why process control is taught in the 5th semester. Isn't it? So you can see that in this particular course you will be using the concept of reaction engineering, sometimes heat transfer, fluid mechanics, even numerical method, optimization, etc. That is the reason why process control is kept towards the end, not in the earlier semester. Okay. So then we started looking at a very simple system in order to understand these balance equations. We looked at our usual case study of tilt and heater where tilt and reactor where CI, FI, TI, these are the input coming in, isn't it? And the output here are CA, F and T. The reaction occurring inside the reactor is A gives R, which is exothermic. So heat of exotherm is removed by the coolant which is flowing through the jacket, isn't it? And then for this particular system we have written all the balance equations except the momentum balance, isn't it? So mass balance given by this particular equation, dV by dt is given as Fi minus F. That is the equation which we have derived. Correct? This is the mass balance. Then we have also derived the component balance and we have obtained the equation which is V dCA by dt is given as Fi Ci minus Ca minus V into K naught e raised to the power minus E by RT into Ca. Isn't it? This is the equation we have derived. And finally we have also derived the last equation which is this V dt by dt is given as Fi Ti minus C plus minus delta HR V into K naught e raised to the power minus E by RT Ca divided by rho Cp and minus UAT T minus Cc by rho Cp. So these three equations actually giving you how the height inside the tank, how the concentration of A inside the tank and how the temperature of reaction mixture inside the tank is going to change with time. Isn't it? Whenever there is a change in disturbance variables, like there are the disturbance variables like Ti. So Ti and Fi are the disturbance variables. If there is a change in Ti and Fi, how my temperature inside the reactor, how my concentration inside the reactor and how my height inside the reactor is going to change with respect to time, I can find out by solving this differential equation. Isn't it? This is what we were saying. Finding the state of the system with respect to time. Isn't it? So in addition to these model equations, there are several other equations one need to look at, and these equations are corresponding to the transport equation or kinetic equations which are given here. Also sometimes you have to satisfy the equations which are coming from the thermodynamics of the system, isn't it? Correct. And towards the end we have also looked at one more requirement which is the date time. So if there is a change in the disturbance variable, the effect of this change in the disturbance variable will not be felt on the system immediately. It will take some time. There is some inherent date time associated with all these systems, all the systems, isn't it? It's not going to happen immediately. Correct. A typical example is if you are having a fluxflow reactor and if you add a tracer at time t equals to 0, effect of this tracer you can find out at the outlet after some time. It is not going to happen immediately, isn't it? So this date time is extremely important in process control. You will see later that typically the system flows are stable, becomes unstable whenever there is even a small date time associated. So it's a most detrimental factor. And we will prove this as we go ahead. Okay. So how we account the date time? We can account the date time. So in this case you can see that this is the translated function we have used here. So what I am saying by using this equation is my T out will have the effect of change in T in only after the TD time. So this particular function is called as a translated function. And how we can deal with such translated function, that also we will see as we will progress. Okay. Finally what we said is There are several difficulties associated with the modeling. These are listed here. We will not go again to this. Let's start with the new topic today. So far what we have discussed is why process control is required. Then we have discussed why model is required, isn't it? And now we are trying to go a little bit inside of that. We wanted to understand, if I wanted to do a control, what are the different variables which are of my interest, isn't it? So typically the variables those are present in the system can be classified into two classes, input variable and output variable. Input variables are disturbance variables and manipulated variables. Now you can ask me which variable I should take as disturbance variable and which variable I should take as manipulated variable. The simple answer to this question is something which you can change yourself is a manipulated variable and something which you cannot change yourself is a disturbance, isn't it? So in this case there are two types, manipulated and disturbance variables. These are the variables which you can change at your discretion. Disturbance variables you do not have any control on. Okay. Output variables are also of two types, measured output variables and unmeasured output variables. Why this measured and unmeasured is important when I am looking at the output variable? Because I wanted to monitor the output variable, isn't it? I wanted to see how my output variables are changing with respect to time. Some of these variables are of direct interest to me, isn't it? For instance, how the height of the tank, height of the liquid in the tank is varying with respect to time. It's an output variable. I wanted to know it, isn't it? Because I don't want my tank to overflow or get dry. Another interesting case can be temperature, isn't it? Whether the temperature is going beyond the set point or not, that I have to check at every time, isn't it? So output variables, whether I will be able to measure them easily or not. This word easily is very important. All the variables are measurable. But in process control, when you are performing the real operation, you want to get the information about these variables immediately. Otherwise, you will not be able to do anything, isn't it? So whether these variables are measurable easily or not, that is what is important. So the variables those can be measured easily, we refer them as measured variables, and the variables those are difficult to measure easily, this we represent as unmeasured variables. And typically whenever we have unmeasured variables which are of interest, we do the secondary measurement in such cases. Instead of measuring that variable directly, we measure an indirect variable which can be measured easily, and then we can correlate that indirect variable to a desired variable. A typical example is concentration is difficult to measure. So whenever you wanted to maintain some concentration at the outlet, you will not be able to measure the concentration easily. It will take some time. If you use some method, some analytical method like HPLC, etc., it is going to take time. It will take 1 hour at least, isn't it? So instead of measuring the concentration, you may measure some indirect variables like temperature, or sometimes you can visually you can observe by using some other equipment. A typical example used in polymer industry where you actually measure the melt index and then you find out the concentration. Okay. So this is a schematic where you can see that there are external disturbances coming into the system are measured external disturbances, unmeasured external disturbances, and then there are variables which are manipulated variables which you can change. So these are the input to the system, and output from the system are measured output which you can measure and unmeasured output which you cannot measure. Alright, let's take a very simple example to understand this again. So this is a typical steel tank reactor example where the inlet is CAI. So CAI is nothing but the concentration of inlet feed. Fi is the flow rate of the feed. Ti is the inlet temperature of the feed. Outlet here is Ca, F and T, isn't it? Again, the reaction mixture is heated by using the steam flowing through this jacket. So in this case, the inlet is Fc and Tci and outlet is Fc and Tco, isn't it? How you control the process? You measure the temperature here by using thermocouple, and if this temperature is different than the set point value, in that case this Ts minus T gives you the error, and based on the value of the error, this controller is going to operate this valve and modulate the steam flow rate to the jacket, and thereby you are going to manipulate the temperature which is there inside, isn't it? Now let's say this particular control loop is for controlling the temperature. Let's say I am interested in controlling the concentration. Then what I am going to do? I am going to measure the melt index. Let's say this is the polymerization reaction occurring here. So I probably will measure the melt index. My aim is to get the concentration, but measuring the concentration is difficult. So instead of measuring the concentration, let's say I am measuring the melt index. And melt index, then I can use a model and I can convert these values of melt index by using a model to a concentration value. Okay, what is melt index? So usually if you look at the polymerization system, there the viscosity, whatever the viscosity, if the polymerization system, if you look at the liquid, if it is more viscous, what it means is more number of polymer chains are there, isn't it? So this particular thing is typically you can observe by using a camera, isn't it? And that is referred as a melting. Sometimes you use a viscometer to calculate directly, and if you do not have a viscometer, then you use the camera and based on that you know. So both the ways are okay. So melt index is typically correlated with the polymer chains, how many polymer chains are there. So it is related to the concentration. But melt index you can measure easily. You cannot measure the concentration. For concentration you have to do something else. Okay, alright. So you can convert this melt index value to the concentration by using model, isn't it? This model could be a regression model, could be machine learning model, whatever, isn't it? Or it could be simply an empirical model. Isn't it? You can use that here to convert this melt index value to a concentration, and then you can see that this Ca is the unmeasured variable here. But we are estimating the value of Ca indirectly by measuring a secondary variable, which is melt index. Correct? So once you get this Ca, estimated value of Ca, you compare this Ca with this set point value that gives you the error, and based on the error, again this error value is given to the controller, and controller is going to change the flow rate of the steam to the reactor, and thereby you are modulating the heat supplied to the reactor, and because of that you can also change the rate of reaction, isn't it? So you can control this concentration through steam flow rate as well. Okay, alright. Now let's gather what are the disturbance variables, what are the input variables, what are the manipulated variables, what are the output variables. Let's look at it. So input variables in this case, CAI, FI, TI, then TCI and FC, these are the input variables. Also I have represented F as an input variable. So is it correct or wrong? Is this F a input variable? Can we call this outlet flow rate as an input variable, or is it an output variable? How? I have written that it is correct. But in which case we can take F as an input variable?
When we manipulate it.
If its value is manipulated, that means if you put a valve here and if you are controlling the value of F, If you are putting some pump which is giving you the fixed value of F coming out, in that case F is a input variable. It's not an output variable because you have decided what should be the flow rate. Isn't it? Okay. Output variables are CA, T, F, TCO and volume of the reactor. In this case, disturbances are what? The input variables like CAI, FI, TI and TCI. These are the disturbance variables, isn't it? Because I am not manipulating them. Correct? And manipulated variables are this FC and F. These are the manipulated variables which I can change with my own decision, isn't it? I can change the flow rate of the steam, I can change the flow rate of the outlet coming out from the effluent coming out from the reactor, isn't it? And unmeasured variable is CA. Okay. Clear? Everyone? Which one? Okay. So rate of reaction can be varied by using temperature. How the rate of reaction is given as K naught for a first order reaction, KCA. K is given as K naught e raised to power minus E by RT. So if you change the temperature, you can change the rate of reaction, you can change the concentration. Okay, is it clear to everyone? Can we go ahead? Yes, no?
Yes, sir.
Okay. Now coming back to a very important slide. So wherever we wanted to perform the control of a given system, there are 5 questions which we need to answer. There are 5 questions which we have to answer. The first question is, what are the operational objectives for which the control system is called upon? Isn't it? So operational objective like whether we are interested in suppressing the effect of disturbances on the system, whether we are interested in stabilizing the process, whether we are interested in optimizing control, isn't it? What objective we are interested in, that we have to specify. The second question is, what are the variables which we need to measure continuously in order to find out the state of the system at any given time, isn't it? So what are the variables which we need to monitor continuously? Okay. Third important question is, what are the variables which we can manipulate in order to intervene inside the system, isn't it? What are the different variables which you wanted to manipulate yourself? So that also you have to find out. The next question is, what is the best control configuration for a given chemical process control situation? So whether you are interested in using the feedback system, feed forward system, inferential system, isn't it? So one of these you have to select, whichever is the best possible case for your problem, that you have to select, isn't it? And the last question is, okay, let's say you have answered all these 4 questions, then you know what manipulated variables are, you know what your control variables are, but the important question is, how much this manipulated variable should be changed in order to have the desired impact on the control variable. This how much is very, very important here, isn't it? I cannot arbitrarily change my manipulated variables, isn't it? Correct. So that is what is asked here. How is this information taken from the measurement is used to adjust the values of the manipulated variable. And we will look at all these 5 questions little bit in more detail as we go ahead. In fact, this last question we will look at little bit in more detail. Okay. Alright. So the first question I have already answered, that is, you have to first find out what is the objective of your control system, isn't it? Whether you are using the control system for ensuring the stability, suppressing the effect of external disturbances or optimizing the economic performances. Also, so if you take an example of a stir tank heater, the objective is to maintain the height of the liquid inside the tank and temperature inside the tank, isn't it? That is what the objective is. So your objective in this case is what? Whenever there is a disturbances, you are suppressing the effect of those disturbances on this control variables C and D. Correct? For stir tank reactor system, If you are looking at a stir tank reactor system, you have multiple operating points, isn't it? Sometimes you are bound to use the unstable operating point. In such cases, you want to stabilize the inherently unstable process, isn't it? That is what we have seen earlier. Is there any question? Let's take the example of the distillation column. So in the distillation column, your objective is to maintain the quality of the distillate coming at the top and the quality of the bottom product coming from the bottom of the distillation column, isn't it? So quality is very, very important, isn't it? So whenever there is a change in the inlet feed to the distillation column, the quality of the distillate and the quality of the bottom product may change. You don't want it to have that, isn't it? So how you can modulate that? You can modulate by manipulating the reflux ratio, isn't it? So by manipulating the reflux ratio, you can maintain the quality of the distillate coming out and you can maintain the quality of the bottom product coming out, isn't it? Correct? Okay. So once the first question is answered, that the objective for which the process control is used, the next important question is to find out which variables you need to monitor, isn't it? So in this case, in a stir tank heater system, you can see that the objective is to maintain the temperature to a fixed value Ts. In this case, you have to measure the actual temperature inside the reactor, isn't it? If your objective is to maintain the height of the liquid present in the tank, in that case you have to measure the height. How you can measure? By using differential pressure sensor, isn't it? So depending on what control variable you are interested in, you have to decide which variable you have to measure continuously, isn't it? So the same thing is written here. You can see that you can measure the temperature by using thermocouple. You can measure the volume or the height of the liquid present in the tank by using differential pressure sensor, isn't it? Sometimes the control objectives are not measurable quantities, isn't it? The example given here, let's say this is what you are trying to maintain the concentration inside the tank. In that case, the concentration is not measurable. In such cases, you measure the indirect variable and convert it into a direct variable by using empirical model. That is what is written here. Now, in the example given here, there is a mixture of pentane and hexane fed to the distillation column. Isn't it? You are separating pentane and hexane using the distillation column. So you get the pentane at the distillate and you get the hexane at the bottom. And there is a disturbance occurring in the feed. So if there is a disturbance occurring in the feed, how the control system can be used in this case in order to maintain the quality of the distillate coming out and the quality of the bottom product coming out. Okay. So this is the example here. You can see that pentane and hexane feed is given as an input to the distillation column. The distillate is coming out at the top. Your objective is to maintain the quality of the distillate coming out. That means your objective is to maintain the concentration of the pentane coming out at the top. That is what your objective is. So what you have to do first? You have to first measure the concentration here, isn't it? So you can measure the concentration here by using composition analyzer. Let's say you have a composition analyzer which can measure it immediately. We will come back to this question whether it is measurable easily or not. But let's assume that you have a composition analyzer, a good composition analyzer which can give you the value of concentration immediately. In that case, what you are going to do? You are going to measure the outlet concentration of the distillate, and let's say the concentration is different than the set point value. In that case, the error will be given to the controller, and controller based on the error value it is going to manipulate the reflux ratio, isn't it? This is the typical feedback control system, isn't it? This is the typical feedback control system. Now if I ask you that change this particular system for a feed forward control system, then can you control the given distillation column by using a feed forward control system? What should be the changes you need to do here? No, you will have to answer because the same thing is there in the tutorial number 2. So what we should be doing if you wanted to develop the feed forward control system here? Anyone?
Steam running.
No, I am not going to go ahead. You have to answer. Then and there only we will go.
So we can add some controller with the steam reboiler. We can add some controller with the steam reboiler so that we can already predict.
So similar feedback you can have here also. That's okay. That's okay. I am asking only for the maintaining the distillate concentration. I wanted to develop a feed forward system. Tell me how it can be done. Feed forward. In feed forward, what is the requirement?
Sir, we have to predict beforehand.
We have to identify the disturbance. What is the disturbance in this case?
Feed.
Feed is the disturbance. So disturbance is the feed here. So instead of measuring the concentration of the distillate, I need to measure the concentration of feed, and that concentration will be measured by the composition analyzer. Then we will have a model in between, isn't it? That model will convert the measured values of the feed concentration to a distillation concentration, isn't it? And that estimated value of the distillation concentration will be compared with the set point, and based on that the reflux ratio will be manipulated. Is it clear to everyone? Right? So same thing is done here. You can see the feed you can measure by the composition analyzer, that will be converted to a distillate concentration. It will be compared with the set point value, and the error, based on the error the controller is going to manipulate the reflux ratio. Correct? Now in this entire discussion there is a problem. There is a problem. Why? Because we are saying that the concentration we can measure easily, which is not true. Concentration you cannot measure immediately. It will take some time, isn't it? So if you try measuring the concentration by using some analytical method, it will take maybe hour, isn't it? By the time you get the value of the concentration, your entire system is already messed up. Not be able to do anything. In control system, whenever you wanted to apply the control, you need to get the output values immediately. Then and then only you can do some interventions. Otherwise, nothing can be done. Correct? So now there is one more control system, what we call it as an inferential control system. What this inferential control system does? Let's say this is the distillation column. Typically you have around 25 to 35 trays are there, isn't it? In a real life distillation column, how people control the distillation column? They don't measure the concentration. They don't measure the concentration. Instead of that, they measure the temperature of first 3-4 trays here at the top. You measure the temperature at different trays, and the temperature at different trays that can be converted to the concentration value by using some empirical correlation. That is what people do. Now measuring the temperature is easy. You can use the thermocouple and within a minute you will get the value of temperature. There is no problem. Concentration cannot be measured within a minute, isn't it? So that is why instead of measuring the concentration, you rather measure a temperature of different trays, and that you can convert to indirect measurement of the temperature you are doing, isn't it? And that you are converting to the concentration, and based on the concentration then you are performing the manipulation of the reflux, isn't it? So the same thing is represented here. You can see we are measuring the multiple temperatures at different trays. We are estimating the distillate composition, and then that distillation composition is used for controlling the, manipulating the reflux. And this particular control system is called as inferential. The word itself is suggesting what we are doing. So we are inferring the actual variable by using indirect measurement. Okay, is it clear? Now let's go to the third question. Third question is, So far we have answered two questions, isn't it? First is the objective. The second question is which variable we should monitor, and the third question is which variable we should manipulate, isn't it? Correct. So for the CS stir tank heater system, the steam flow rate is the manipulated variable, outlet flow rate is the manipulated variable, isn't it? In a distillation column, the reflux ratio is the manipulated variable. So depending on your system, you have to select the manipulated variable, isn't it? Correct. Now let's move to the fourth question. Which control configuration is best for your system? Isn't it? There are multiple control configuration possible: feedback, feed forward, differential. Whether you wanted to control F or Fi, isn't it? If you wanted to maintain the height inside the tank, you can manipulate outlet flow rate as well as you can manipulate the inlet flow rate both, isn't it? So there are multiple options are there. Out of these multiple options, which option is the best for your system, that you have to select. Okay. Typically we have one input and one output, and you will see that most of the cases which we are going to study in this particular course will have single input and single output. Okay. But real life system, you will see that there are multiple input and multiple output. I don't know whether we will get time. If we will get the time, then probably this multiple input and multiple output system we can see towards the end. I am not sure whether we will get or not. So there is a lot of interaction occurring when there are multiple loops are there, and it is much more complicated than this. But mostly in this particular course, since this is the beginner course, we will only look at single input and single output. We will not touch upon this multiple input and multiple output. Okay, is it clear? But real life process control, you will see that will be mostly this multiple input and multiple output. Clear, everyone? Okay. Coming back to the most important question. Yes.
So in the slide you mentioned that distillation has three options: feed forward, inferential, and feed. But in the stir tank you mentioned there are only two options. Why is inferential not available in there?
Why you require inferential training?
I was not.
I will get back to the point. Tell me what inferential you will do here.
When we don't know what is coming in, what is the composition, must see. What is the same composition of feed?
Here you are saying that instead of here also in a way it is a inferential itself, isn't it? You are not measuring the actual variable. Rather than that, you are measuring the net index, and that you are using to infer the outlet temperature. So in a way, this is actually the inferential. Okay, coming back to the last question. This is a very important question. Okay. Now in this particular question, what we are trying to answer? We are trying to answer how we are going to manipulate our manipulated variable so that it will give me the perfect control. In what way I should manipulate? Should it be proportionally I should manipulate, or should there be any other law to manipulate? Isn't it? Correct. So that part we are trying to answer. Let's take the example here. It's a stir tank heater system. The inlet is Fi and Ti. Isn't it? Our aim is to maintain the height, and our aim is to maintain the temperature of the liquid present in the tank. So in this case, let's take the simple case where we wanted to maintain the temperature inside the tank, isn't it? So we are going to measure the temperature by the thermocouple. So typically all the measurement units are represented by the second letter T. So for instance, temperature measurement. So temperature first letter is with respect to T, and the second, all the measurement units are represented by the second letter, which is T. So for instance, if we measure the concentration, I would have written this as Ct. Okay. Similarly, the controller is represented by the second letter C. So here TC is nothing but temperature controller. Let's say if I wanted to write about the pressure control, in that case I would have written this as PC. Level controller I would have written it as LC. Okay. So these are the terminologies commonly used when you are representing the PNID diagram. Okay. Alright. So in this case the temperature is measured, and this measured value of the temperature is compared with the set point, and based on that the error is obtained, and depending on the error value the steam flow rate is modulated. So when we are modulating the steam flow rate, actually what we are manipulating here? We are actually manipulating the amount of heat supplied, isn't it? So we are actually manipulating Q. We are manipulating Q in a way, isn't it? Now the question here is, let's say if there is a change in Fi and Ti, if there is a change in Fi and Ti, in order to maintain the temperature T constant, isn't it? How much this Q should be changed? In what way this Q should be changed in order to maintain the temperature inside the tank same as the desired set point, even though there are disturbances Fi and Ti? This is the question we are trying to answer. Very simple case. Very, very simple case. You might be saying that every time we are coming back to the same system. We are purposefully coming back to the same system so that you can correlate what we have studied so far, isn't it? And you will see that as we progress, this system is going to become more and more complicated as we go ahead. Okay. Now, for this particular case, what are the equations? What are the equations? If I have to write down the mass balance, what will be the mass balance? dV by dt is given as Fi minus F. And what about the temperature? Temperature V dt by dt is given as Fi into Ti minus T. Ti minus T. There is no reaction occurring, isn't it? Heat is supplied, so plus Q divided by Rho. This is what the expression we are expected to get. I will go back to the same model equation. Remember I told at that time that these equations we are going to use directly. Now, we are not going to derive it again and again. So what equation is expected to get? We will have V dt by dt Fi Ti minus C. This term is not there because reaction is not occurring, isn't it? So this term is not there, and instead of this I am just representing Q here. Here the heat is taken out. Remember in this case the heat is taken out. But when heat is supplied, in that case this will become plus sign because heat is supplied. Isn't it? So Q divided by Rho C. Correct? So same expression we have written here. So V rho Cp dt by dt F rho Cp Ti minus T plus Q. This is the expression we are expected to get. Correct? Now write down this equation. Write down this equation at steady state. Write down this equation at steady state. Here in this case we are assuming that this flow rate is constant. Flow rate is not changing. Only the Ti is changing. And based on this Ti, I wanted to see how the temperature inside the tank is going to change with respect to time, and that can be represented by using this equation, isn't it? I can find out how the temperature inside the tank is changing with respect to time if there is a change in Pr, if there is a change in Pr, isn't it? I can write down this equation for steady state. At steady state, so remember this particular setup is running, isn't it? At time t equals to 0, the steady state is already achieved. That means the temperature is already achieved the steady state value, isn't it? At time t equals to 0, I have added the disturbance, and because of the addition of the disturbance, my entire system is messed up after time t equals to 0. So before time t equals to 0, my system is at steady state. So at steady state, this term becomes 0, and right hand side will become what? F rho Cp. This Ti will become a steady state value of the inlet, Tis minus set point Ts, isn't it? Plus Qs. Here all the subscripts are steady state values. Correct? So this is the equation which we have obtained at steady state. So this is what is shown here. You can see the Ti is at a steady state value Tis before the time t equals to 0, and time exactly time t equals to 0 I have added the disturbance in Ti, and this Ti is changed from its steady state value Tis to some new value. In this case there is a step input I have given. In this case I have given a step input. I have changed my inlet temperature Ti to a new value, some new value from its earlier steady state value of Tis. Now because of that, what will happen to the outlet temperature? What will happen to the outlet temperature? You will see that the outlet temperature if you look at, here I have plotted T minus Ts, but if I would have plotted only T, in that case the outlet temperature will be, before T equals to 0, the outlet temperature will be steady state value Ts, and exactly at time T equals to 0, because of this disturbance my outlet temperature will also mess up, and that will increase and it will settle to a new steady state value. This is what is going to happen, isn't it? I have represented that deviation directly here in the form of T minus Ts. So this should start from 0. This should start from 0. Okay. So now what is happening here? This is the steady state value. This is the equation which is at steady state, and this is the general equation which is applicable to a dynamic situation. I can subtract this equation from this. What we get is V rho Cp d T minus Cs by dt equals to F rho Cp Ti minus Tis minus T minus Ts plus Q minus Ts. Now why we have done this? You will see that in this course, whenever we are writing the differential equations, we always write the differential equations in deviation form. There is a reason why we are doing it in a deviation form. When we will look at the Laplace transform, then you will understand more why deviation form is used. Because if you take the Laplace transform of derivative, isn't it? You will have some initial condition coming in, and all these initial conditions become 0 if you take the deviation form. That is the advantage. Okay. So that is the reason why in this course all the equations you will see we write in a deviation form. So this is the equation which we have written in a deviation form. Here you can see that this dt minus Ts by dt, this is nothing but what? The deviation of the temperature from its steady state value, how that is changing with time, isn't it? We are actually interested in getting this T minus Ts equals to 0, isn't it? We are interested in getting T exactly equals to Ts, and right hand side also this Ci minus Cis is nothing but what? The inlet temperature given in a deviation form. This is the actual outlet temperature given in a deviation form, and this Q minus Qs is the amount of heat supplied in a deviation form. So how much increase from the steady state value is there with respect to T, Ti and Q, that is represented here by these three differences. Is it clear? Okay, so this is the equation which we have obtained. My aim here is to maintain T to Ts. Now what is this Q minus Qs is? This is the deviation in the manipulated variable. And this Q minus Qs is the manipulated variable which is in your hand. This is the variable which you can change. In this entire equation, nothing you can change except this last term. This is the last term which is there in your hand. Now the question here is, in what way this Q minus Qs you should change in order to have this T minus Cs equals to 0. That is what the question is. Depending on, so see this T minus Cs, this is the error. You are going to measure the error. Remember the temperature you are measuring by using thermocouple. You know your steady state value. So T minus Cs, which is the error, you know the values of this error. Now depending on the values of the error, how I should change this Q minus Qs such that this T minus Cs becomes 0. And there comes different control laws. Okay. Whether this T minus, whether this Q minus Qs should be proportional to T minus Qs or something else should be done. As a layman, that is the first starting point I should take, isn't it? I should manipulate my variable proportional to the value of the error, isn't it? So more is the error, more the manipulation I am going to do. Less is the error, less manipulation I am going to do. That is natural, isn't it? So the natural law in this particular case is I should manipulate my variable proportional to the error, isn't it? And when this particular law is used, then the controller is called as proportional controller. Then the controller is called as proportional controller. So you can see that in this particular equation, you can see that Q minus Qs is proportional to T minus Cs, isn't it? Correct? So as the temperature is increasing, as the temperature inside the tank is increasing, then I should decrease the value of amount of heat supplied, isn't it? And that is the reason why minus sign is coming into the picture here. Because as T is increasing, this Q minus Qs should decrease, isn't it? So that is why the minus sign is coming into the picture, and this alpha is the proportionality constant. This is referred as proportional gain. We will see little bit more detail of this gain term later, isn't it? So simplest law here is the Q changes proportionally to the error T minus Cs. And if I put this alpha into T minus Cs in this particular equation, this is the equation I am getting. This is the equation I am getting. Okay. Now in this particular equation, I am interested to make this T minus Cs is 0, and if you look at this particular differential equation, you can get T minus Cs equals to 0 only and only if your alpha value is infinite. You can get this T minus Cs equals to 0 only when your alpha is infinite. What it means? Alpha is nothing but what? Controller gain. It's a strength of the controller, and this value you have to specify, isn't it? You have to specify. Now this particular law is saying that you should specify a very large value. Based on the mathematics that looks okay, but in real life it is not okay. Why? Because this entire thing is based on your measurement of T minus Cs, and your measurement may be flawed. You might not be measuring the correct value, and if you are using a very large values of the controller gain, instead of stabilizing the process, you may end up with destabilizing the process. So you have to be conservative in using the value of alpha. But there is a problem. If you use a small value of alpha, you are not going to eliminate the error completely. You will always have the offset. So with this control law, there is a problem. The problem is, in a proportional control, you always get the offset. You will not get the perfect control at all. Proportional control is always comes with the offset. What is offset here? Offset is nothing but the steady state error. Remember, in this case, my objective is to maintain T minus Cs equals to 0. But I am not going to get 0 unless I put alpha equals to infinity. And if I don't put this alpha equals to infinity, I will always have the offset. I will always have the steady state error. So proportional controller always gives you a steady state error. It will never give you a perfect control, isn't it? That is the drawback. So we will stop here. The next question here from this particular point onward is how I can get this steady state error 0. That is what the question is. Okay. And we will try to answer this question in the next class. So slides are there in this book. You can get it. Only the hard copies are allowed. Another thing which I wanted to tell you is the tutorial will be held at workshop 101. That is the first room. If you are entering the workshop, the first room you see on the left hand side, that is WF 101. We will have a tutorial on Monday and Friday, 2 to 3 in workshop 101.